Hi, everyone. Thank you for coming to our presentation on black box explanation for face verification. This work has been done by the Catholic University of Chile. So this is our agenda for today. We start with the motivation and we explain the methods. We show some experiments and finally some concluding remarks. So face verification is as follows. You have two input images, the enrolled and the proof images. And the idea here is to compute a score. So if the score is high enough, we say that these persons are the same. But if the score is low, we say that these persons are different. So sometimes this facial matter is seen as a black box. Explainable face verification arises from the need to understand the facial matter models. This methodology can help us to interpret and visualize the models that are often considered as black boxes. In explainable face verification, the task is to answer how relevant are the parts of a proof image to establish the matching with enrolled image. So this is the idea. We have the two input images that they are processed and analyzed in combination with the facial matter to establish the saliency map. Here we can see the most relevant part for the face recognition algorithm. So let me show you the method. We have the two input images and we make some perturbation of the second image in order to obtain a modification of this. So we compute the score of the original pair and we compute the score of the pair with the modification. So we analyze the difference between these two scores in order to compute the saliency map. So here, one of our approaches, we start by removing one part. This is our perturbation, and we remove each part using a sliding window method, and we compute here the difference of the original score with the new score that is perturbed. We can see that the difference here is very important. That means that these are the most relevant parts for this facial matter. We can repeat that by adding a second region that is relevant in combination with the first one, and we can add this third, the fourth, and so on. And here are the parts that we can remove, and these are the scores that we obtain by removing one region after another. So these are our two saliency maps obtained by removing one region and by removing one region after another. And of course, we have a dual approach that is obtained by adding one region and by adding one region after another. We can combine that in order to have a switch between adding and removing, and we can compute the average of the first four methods. So let me show you the experiments. Here are some synthetic images with different qualities and occlusions. We compare these images with the rest of this, and we can see the saliency map of several state-of-the-art methods, and these are the results that we are obtaining with our methods. We can see how stable are our results. These are the second experiment, real face images with different facial expression, poses, and occlusion, and we can see the relevant part of each pair of images. So let me show you the conclusions. We propose 6 different approaches to build saliency maps, avoiding any manipulation inside of the face recognition model. Our methods remove and aggregate relevant parts of the face and measure individual contribution of these parts and in collaboration as well. Using these methods, we appreciate which are the most relevant face areas that an algorithm considers to carry out the recognition. Our approach can be used to evaluate commercial off-the-shelf face recognition methods as well. So we invite you to see our Google Colab in our web page, and thank you for your attention.